Okay, this is for Astronomy 320. It's July 24th, 2020. And so right now up on your course module you have the new online lecture number 8, and I made it through Tuesday, and this is PowerPoint number 16 that we're looking at. So everything's been uploaded. You can download the online lecture that we're going to look at, this one right here. It's up on the on Canvas. Okay, so we're skipping up to Chapter 16 now. So basically, Chapter 16 starts off with energy. Energy is probably the single most important thing anybody studies in college, and it's sad some people don't even study about it, because it's like so incredibly important. It can explain just about everything if we understood it well enough. Energy, basically, for our purposes, it's the ability to do work. Energy is the ability to do work. So the chemical energy stored in your gas tank can do work on your car and move it down the road. So basically, your car, through a lot of mechanisms, is going to convert the gasoline that's in your tank into motion of your car. Energy cannot be created or destroyed. Energy can be transformed from one form to another. Your car converts chemical energy, potential energy. It's potential if it's sitting out in your driveway or out in the parking lot someplace. It's potential energy then. But then it can be turned into motion energy, which is also called kinetic energy. So we can transform energy from one form to another. When you turn on a light switch, you're converting electrical energy into light energy. Okay, there's a number of different ways to convert energy. A number of different types of energies can be converted into other types of energies. So first of all, I got that misspelled, don't I? So this is an example. This is how basically we get most of our energy in Sacramento, and a lot of our energy anyway. We've got the Thomas Dam, or the Nimbus Dam. We've got the Folsom Dam, and here's the kind of the way they work when they convert energy from one form to another. So it rains, okay? It rains in the Sierra, and it snows in the Sierra, and the snow melts, and the water rushes down the American River, and it comes to dams that people have built. And so water flows down the American River, and it's held in place by dams like the Nimbus Dam and the Folsom Dam. So here it is, held in place for now. So what good does it do us? Okay, this is potential energy. This water has a lot of potential energy. It's gravitational potential energy because it's so high. We can let it fall. Okay, so transformation of energy from one form to another. Releasing the water turns its energy from potential energy to what we call kinetic energy or motion energy. Now it's in motion. Okay, well, again, how does this help us? Can you run your car, your watch, or your TV with this kinetic energy? Well, not the way it's set up right now, but just wait. So the flowing water, because it has kinetic energy, can make a turbine rotate like a water wheel. It flows over it, and it causes it to turn. Now the real turbines don't quite look like this. Okay, rotating turbine, that's mechanical energy. So we've converted the kinetic energy into mechanical energy, the rotating turbine. It could also be called rotational kinetic energy as well. This rotation can be considered rotational kinetic energy or mechanical energy. The rotating turbine can be connected to a large magnet. Okay, so there's a magnet at the north-south sides, and we can engineer it so that it goes back and forth. Okay, it goes back and forth. This thing rotates. Its rotation causes the magnet to move back and forth. Still, how does this let us cook food in our microwave or anything like that? Well, here's what you do. You put a coil of wires around the magnet, and there's electrons in there, and you're changing the magnetic field on the electrons. Okay, the electrons don't like that. They're going to start to move to create their own back magnetic field to cancel out the changes you're imposing on them. But that's good. We get them to flow, and it's like an AC circuit. It's alternating current. You go one way, the electrons are going to flow one way. You go the other way, but we've got a current. We've got an electrical current. We've got electrons flowing. Okay, again, we started with the potential energy. Now we're all the way down to electrical energy. And so electrons, so if the magnet oscillates back and forth in a wire coil, the electrons will react and start to flow in an electrical current. We just generated electricity, and this is just a YouTube video showing you how, you know, the actual power plants, how dams work to generate electricity. It's about 1.1 1 minute and 55 seconds, a little less than two minutes. Okay, well now you hook up the electrical energy goes through all these little power towers, and it goes to your house. And now it's time for you to study for your Astronomy 320 class, so you flip your switch, converting electrical energy into light energy. So it all started up here with the potential energy of the water held by the Nimbus or Folsom dams, and now it's all the way down here in your house, and you're using it to work on your 320 homework or whatever you have here for this class. Then here's another video to watch if you want to. Okay, now that was about energy. Now 16.2, mass, energy, and the theory of relativity. And you might think, well, theory of relativity, we're not going deep at this. That's kind of misleading. We're not going into the theory of relativity. We have a little bit, a touch of the theory of relativity, but it's just some small little part that's easy to understand. Okay, here's what we know about energy. So let's go. Okay, so what is energy? Energy is the ability to do work. Okay, what else do we know about energy? Well, what else do we know about energy? It's right here. Energy is a conserved quantity. Energy cannot be created nor destroyed, but energy can be converted into matter. Also, matter can be converted into energy. Okay, at the center of the sun, at the core of the sun, matter is being converted into energy. That's how the sun generates energy. And then the part about energy being converted into matter, maybe that's the Big Bang. Maybe everything was energy. There was no space. There was no matter, there was no mass, there was nothing you could touch. It was just all energy, and then boom, something sparked it, and we had the Big Bang, and suddenly we had hydrogen and helium atoms running around. Okay, stars generate energy through fusion. So you start with 4 hydrogen nuclei. Those are just simply protons. 1, 2, 3, 4 protons. You end up with 1 helium nucleus, which is 2 protons and 2 neutrons. The 4 hydrogen nuclei combined have more mass than the resulting helium nucleus. What happened to the missing mass? It was discovered that mass and energy are equivalent. The missing mass was converted into energy. Energy is equal to mass times the speed of light squared. E equals mc squared. Energy equals mass times the speed of light squared. There's what the speed of light is. Usually you have it as 3 times 10 to the 8th meters per second. To get an idea of what it is, actually, it's 186,000 miles per second. If you can, the numbers are mind-boggling. And then, who made this incredible intellectual leap? I forgot his name, but I think it starts with an I. What is his name? Albert Einstein. He did it. Okay, so that was another, I mean, just so many things he discovered. So, right here, what is Einstein's famous equation showing that energy and mass are equivalent? E equals mc squared. Okay, now this is right from your textbook. I took it out of your textbook. So you got these mass of these different things. So you got the proton, neutron. Protons are +1, neutrons are 0, electrons are -1. And then we got these neutrinos. Look at that. The mass is uncertain, but it's going to be less than 2 times 10 to the -36. Okay, that's like, you have to go 0.036 times. 0.0000. You got to say 0 36 times, and then you finally get to the 2. That's how small the mass is for a neutrino. They thought neutrinos had no mass at one time, but it's very, very small. Remember that. That becomes something comes up later. Okay, now, in the nucleus, like a helium nucleus, you've got four constituents. You've got the 2 protons, and you've got the 2 neutrons. Okay, well, don't protons repel each other? You would say, well, how can we get them together? They're going to repel each other. They're going to shoot apart. Well, no, here's the thing, though. They will shoot apart when it's the repulsive electromagnetic force, but over incredibly short distances. Okay, this is a graph. Force, and this is distance from the center of the nucleus. If we can get the two protons close enough together, then the strong attractive force is stronger than the repulsive electromagnetic force, and they'll stick together. Now, if we can't get them too close together, yeah, the repulsive force here in the green, that will win out. But we get them close enough together, like this, not much more than the size of a nucleus, then they will stick together. Okay, so that's how you got to get them. And it takes extremely high temperatures to get them moving so fast that they can't avoid each other. So it's like they're flying around so fast that they're heading right towards each other, like 2 people driving 20 miles per hour and they see each other, and it's 4 seconds before they're going to have a head-on collision, they probably avoid each other. Then you got two people driving 100 miles per hour at each other. They see each other 4 seconds before head-on collision. Maybe they aren't able to avoid each other. Same thing here. If they move extremely fast, they may not be able to avoid each other. They get too close, then the strong force takes over, the attractive strong force. Okay, so here we go, fusion versus fission. Fusion is the fusing of atoms, of nuclei, okay, to make a bigger one, okay. Fission is the splitting of the atom, okay. Fusion is fusing nuclei together to make bigger nuclei. Fission is splitting the atom. Okay, fusion and fission. And so you hear about them both. We're talking about fusion here. The sun generates energy through fusion, through fusing nuclei, through bringing them together. Oh, and then we got the question here. Okay, what is the difference between nuclear fusion and nuclear fission, or nuclear fission and nuclear fusion? Well, fission is the splitting of the atom. Fusion is fusing the atom together, and there's a difference there. It's important. If we go down here, ways, how far do we have to go? Okay, see, through fusion, the sun's going to fuse hydrogen into helium, and then later on it's going to fuse helium into beryllium, and it's going to get carbon. But that's where the sun stops. But other stars can keep going, generating more and more energy through fusion until you get to here. Then it's all over. You can't get any more energy through fusion. The rest of these you can get energy by splitting them. Okay, so iron is the end game there. Okay, so now there are different parts of this. The first thing that's going to happen is you got the two hydrogens. They're just two protons. That's all they are, two protons. Now, one of those protons gets turned into a neutron. That's a neutron there. That red one's a neutron, the blue one's a proton. When one of these protons, say that one right there, got turned into a neutron, it emitted a positron, which is like a positive electron, and a neutrino that we just talked about a little bit ago. There's where the neutrino comes from. So that turned it into a neutron. But it's still hydrogen because it's only one proton. Okay, then what happens is that guy we just generated up there with the one proton and the one neutron runs into another hydrogen. Okay, now we get what we call helium with two protons, and we give off a gamma ray. The gamma ray actually came about when this positron runs into an electron. They annihilate each other. It's matter-antimatter type situation. So when they annihilate each other, that has mass. The electron has mass. So we just turn mass back into energy. We turn it into a gamma ray. So it's not really coming from this. It comes from this guy leaving and then running into an electron. But now we got this helium with only one neutron, but that's not normal helium. So what'll happen next is two of these heliums we just made up here will come together. We'll end up with one helium that's the normal type with the two neutrons and two protons, and then these two guys were just kind of like, I guess you call them catalysts. They're involved in it, but basically what you ended up having 4 hydrogen atoms, 2 stayed hydrogen, and 2 turned into neutrons. And now you've got this guy. But this guy, here's I think the next picture. So you started off with 1, 2, 3, 4 hydrogens. You ended up with 1 helium. Now a bunch of stuff happened along the way. Yes, indeed. So here's where the 2, 3 come together. You see there's a gamma ray coming off of here. You got a gamma ray coming off of here. There's where your neutrino comes off. So your neutrino came off here, and your positron came off here. But the whole big picture is this: 4 hydrogens became 1 helium. This helium has less mass than the combined masses of these 4 here. Where did that mass go? It got converted into energy. Okay, so how does the sun generate energy at its core? Through nuclear fusion. Okay, and so what it does is it takes 4 hydrogens and combines them into 1 helium, That's with so 4 hydrogens are 4 protons, 1 helium is 2 protons, 2 neutrons, and energy was emitted as a result, as well as neutrinos. Okay. And then basically, the book talks about this a little bit. Fusing helium into carbon, triple alpha process. So basically what happens is 2 of these heliums will come together, give you beryllium. This is very unstable. It'll break apart almost right away. You need another neutron in there to make it stable beryllium. But if you're fast enough, at 100 million Kelvin, see this one here happens at 10 million Kelvin. Actually, to have a stable sun, it has to be at 12 million Kelvin, but it first happens at 10 million Kelvin. And then you get the heliums, and they can combine to give you beryllium, but if you're not fast enough, this will break apart into 2 heliums. But if you stuff another helium in there, then you get carbon. Carbon with the 6 protons and the 6 neutrons. Okay, and then we can go through other things, like for example, there's carbon, there's oxygen, and we get silicon, then carbon, oxygen, and oxygen. We can get silicon with a different number of protons. We get iron if we go silicon and silicon, we get iron. So it goes up and up and up. Okay, we can start, but our sun can't fuse these. Our sun's not big enough to reach the temperatures necessary. Our sun will be able to get to this temperature to get carbon, but that's it. It'll become a big ball of carbon. Okay, evolution of a massive star. So basically here you got the non-burning envelope of hydrogen. You've got hydrogen fuse. See, these are all these shells. This is where our sun will get to and stop. But bigger stars can start fusing carbon and then getting oxygen and neon and all these other elements, including iron, and it's iron ash because that's as far as you can go. Iron ash. We'll get all these other elements, but we'll end up with iron ash, and that's the end game. That's it. You can't go any further than that. Okay, so this is just extra information we may run into on the next video. I don't know. All right, now the sun is what we call is in equilibrium. As long as the sun has plenty of hydrogen to fuse into helium at its core, it will be stable. It's been fusing hydrogen into helium, burning hydrogen for about 5 billion years with a B, and it'll be doing it for about another 5 billion years with a B. The sun relies on hydrostatic equilibrium to remain stable. So gravity's in the blue, so there's gravity in the blue. It's trying to shrink the sun down to that little dot right there. That's what gravity wants to do, wants to shrink everything down. But as long as we can fuse hydrogen and the helium at the core will push back out. So we'll get this pushback, and so as a result, the inward pull and the outward pushback is going to be stable. Okay, as long as we can start fusing hydrogen, so the gravity shrinks it down, temperature increases to the point where hydrogen's burning at a rate to generate enough outward pressure to balance the gravity. Okay, so right now we're balanced. Gravity is trying to shrink the sun down as small as possible. Pressure outward balances the inward pull of the gravity, and the sun is stable. Okay, now after energy is generated at the core, it must travel to the surface. It takes like thousands of years. Like I should have looked it up. It takes a long time once the energy is here to get to the surface. Okay, the first mode of transport is through radiation. Okay, so this is called the radiation zone. He's got it as a radiative zone. I've never heard that word used. When I say radiation zone, I mean the same thing the book authors call it radiative zone. I have no idea. I like radiation zone. That's all I've ever seen my whole life. Right. It is so hot in the radiation zone that electrons have been stripped away from the nuclei, so are not absorbed. So the radiation is not absorbed. It's not well worded. The electrons here is so hot that the electrons don't stay with the nuclei. So that means the radiation it's clear to the radiation, because the electrons won't absorb them because they're not with a nucleus to go to higher energy levels or anything like that. Now, when things cool off up here, then what happens is the electrons do recombine. Okay, and when they recombine, then they will absorb the radiation and go to higher energy levels. But that also heats things up. And what happens is the warm material rises, okay, gets to the surface, then out comes radiation again, okay, but then the material that emitted the radiation towards the Earth and towards the rest of the solar system, it cools down, then it falls, then it heats up, absorbs more electrons, and so basically energy is carried to the surface of the sun here through the convection zone. So from the core, where the real big business is taking place, where we're fusing hydrogen and helium to generate energy, then through radiation, gamma rays, but remember, gamma rays interact and stuff like that, and they end up being other types of radiation with longer wavelengths and less energy. It gets like one gamma could give you a bunch of other different types of radiation with less energy they would add up to what the gamma ray had, but maybe less. Okay, so things cool off by the convection zone and the radiation is absorbed, heating the material. Warm material rises, emits the radiation to surface, cool and falls, and the whole process repeats. So that's the radiation zone and convection zone. Let's see what I want to do here. So I want to go to this. All right. So why is the sun stable? Okay. Why is the sun considered stable at this moment in time? Because you've got hydrostatic equilibrium. Because the gravity in heats up the interior until it's burning hydrogen at a rate that it's pushing back out. Okay, and it gets to the point where it's balanced. You got a balance there, stable, balance. Radiation zone, that's where the radiation moves through. It's hot. The electrons are separated from their nuclei, so the radiation can just zoom right through. But in the convection zone, the electrons have recombined, and now they absorb the radiation, and as a result, the radiation doesn't get through so easily. Okay, we're up to helioseismology, I believe. Helioseismology. Okay, variations like sound waves travel through the interior of the sun. So you've got these waves bouncing back and forth through the interior of the sun, causing surface vibrations. Okay, this causes the surface to vibrate like a big spherical drum. Much like earthquakes on Earth allow us to make deductions about the interior of the Earth, these vibrations allow us to make deductions about the interior of the sun. Study of the amplitude and cycle length of velocity changes provides information about the temperature, density, and composition of the layers through which the waves pass before they reach the surface. Helioseismology is the study of these vibrations. Okay, so that's what helioseismology is. It allows us to do all this stuff. And so in PowerPoint, or I'm sorry, in this guy here. All right, so what is helioseismology? The study of the surface vibrations on the sun. What can the study of helioseismology tell us about the interior of the sun? Well, we've got some of them listed there, I think, didn't we? So temperature, density, composition of the layers through which so basically study amplitude, cycle length of velocity, and provides information about temperature, density, and composition of the layers through which the waves pass through. Okay, so there we go. Solar neutrinos. We talked about neutrinos already. Neutrinos are extremely. It should be R. It's not going to be fixed on the one you download, though. I'm not going to read. I don't know if I'll read up this or not. Are extremely small mass particles that travel near the speed of light. They interact with almost nothing, and there are more than 1 trillion of them passing through your body at this very, very moment. That's how little they're all over the place. There's billions of them, but you saw what small mass they had. They're like almost massless, completely massless. Neutrinos resulting from fusion reactions at the core of the sun offer still another method scientists can use to study the sun. But because they rarely interact with anything, they are difficult to detect. So the one your book talked about was one method that they first tried to use. First of all, you got to go deep underground. Why? Because you don't want radiation from anywhere, the sun especially, affecting your results. Because radiation could interact with your detector, and you might think that's a neutrino. So you go deep underground where the Earth's layers block the radiation. So this is deep underground someplace. So one way to detect neutrinos is through their rare reaction or interaction. It should be interaction. Maybe reaction. It should be interaction probably with chlorine. So liquid chlorine. This I don't know for sure. This could be heavy water or liquid chlorine. I don't know what type of detector this is. Solar neutrino detectors are placed deep underground to protect them from false results due to radiation. When a proton becomes a neutron, it emits a neutrino. Okay. Well, remember way back here? See, look, one of these became, actually, let's go to the other picture. This one here. So one of these became a neutron. Proton. This blue one here is still the proton, but this became a neutron. When this proton turned into a neutron, it emitted a neutrino. Okay. Okay, when a neutron absorbs a neutrino, it can become a proton. It can go both ways. So, in this case, chlorine has 17 protons in its nucleus. So here's a periodic table. There's chlorine. It has 17 protons in its nucleus. That's what makes it chlorine. If one of its neutrons that it has 17 protons, it has, who knows, a bunch of neutrons. If one of those neutrons gets turned into a proton, you've got argon. Okay, you've got argon, because you turn one of your neutrons into a proton. You don't have 17 protons anymore to make yourself chlorine. You have 18 protons now to make yourself argon. Chlorine has 17 protons in the nucleus. When one of chlorine's neutrons becomes a proton, the nucleus becomes an argon nucleus. The number of argon nuclei are then counted to estimate the number of solar neutrinos that pass the detector. Okay. Now, I think, if I remember correctly, that first one they were trying to do, it was smaller, a lot smaller. But one of the billions and billions of neutrinos that passed through the large tank of chlorine, it was expected that 3 or 4 neutrinos would be detected per week. I remember hearing that, reading that over and over again. Okay, so it was a smaller tank. So they're doing their calculations, and they should have recorded 3 or 4 neutrinos per week. But there was a huge surprise when less than half, probably close to a third, the expected neutrinos were detected. They only detected something like a third of the expected ones. Okay, does this mean the solar theory was wrong and it was time to return to the drawing board? Remember these guys we had up here? Okay, why aren't we detecting these neutrinos? Where are they? We're not detecting them at the rate we should. We think we know the science, and so now we got a big problem. We got to figure this out. Okay, does this mean the solar theory was wrong and it was time to return to the drawing board? It turned out that the theory was correct and a new discovery was made. The detector was looking for what we call electron neutrinos, which are the type that would originate from the sun. But neutrinos have the ability to change into other types of neutrinos on their way to the Earth. I think they're called, one's called a muon neutrino and another one's called a tau neutrino, but your book doesn't mention it, so I think it's not important. But I could have gone and looked it up on Google. The detector would not have detected these other types of neutrinos. There's 3 types. So that's maybe why they're only getting a third, because 2/3 of the neutrinos on their way to Earth oscillated and turned into another type of neutrino. All right, the Sudbury Neutrino Observatory in Canada was the first one designed to capture all 3 types of neutrinos. Okay, now it was much larger. It was built 2 kilometers underground. 1,000 metric tons of heavy water. So there's different ways that heavy water, basically heavy water, regular water is just oxygen with 2 hydrogens, and neither one of the hydrogens has a nucleus, as a neutron in its nucleus. Heavy water, you've got the oxygen, you got one of the hydrogens, it's by itself, but the other hydrogen has a neutron in the nucleus with it. That's why they call it heavy water. It was much larger and was expected to detect up to 1 solar neutrino per hour. So now we're looking for all 3, not just the electron neutrinos, but all 3. Astronomers were relieved when this was exactly the result they found. And about 1/3 of the captured neutrinos were electron neutrinos as predicted. You got 3 types of neutrinos, and on the way to the Earth, you can oscillate, flip, turn into another type of neutrino. And I guess it's pretty random, and so as a result, we would expect to only get 1/3 of electron neutrinos, and then the other 2/3 would be the other types of neutrinos. Oh, that's it. Okay. So, what are neutrinos? Well, they're close to being massless. They travel at the speed of light. There's billions of them traveling through your body at this very moment as you sit there, trillions of them, really. Okay, so we had what the neutrinos were. What is the great mystery called the solar neutrino problem? Your book doesn't call it this, but I've heard it called this plenty of times. The solar neutrino problem is that we were detecting too few neutrinos than we would expect, considering what we think goes on at the core of the sun. All right, what groundbreaking discovery finally solved it? That neutrinos come in 3 types, and that on their way to the Earth, they can change or oscillate. They call it neutrino oscillation. They can oscillate into other types of neutrinos, which were not set up to be detected by that first detector. Well, we actually built a detector that was much larger and was capable of detecting or capturing all 3 types of neutrinos. Then we got what we were expecting, and the solar theory stood the test. Okay, that's everything.
Okay.
I'll probably try to have another one of these up here by this end of this weekend. Quiz on Tuesday. I guess I'll use this to get ideas for the quiz for Tuesday. Then I think we have our final on Thursday. Isn't next week the last week? I think I'll go look. All right. So let me talk to you later because it's going to take a long time to upload, and I'll talk to you soon.